Okay, so now let's talk about the exergy of the gas inside the cylinder นะครับ so if we have a gas inside the cylinder here we can extract the internal energy of the gas to the useful mechanical work by the expansion process, right? So let's say for this case, if we have the gas with the initial pressure of P and temperature of T, so we can let it expand to push something, right, to do a useful mechanical work. Okay, so the expansion process will reduce the pressure inside the cylinder, right, and also reduce the temperature inside the cylinder of the gas inside the cylinder. Then I can let the gas expand to push something until the pressure of the gas go down to equal to the pressure of the environment, atmospheric pressure, right, P0, and also the temperature go down to equal to the temperature of the atmospheric condition. Okay, at that point I cannot further expand the gas because the pressure inside the cylinder will be equal to the pressure outside, and I got the force balance, right? So I cannot extract any more energy from that point, any more internal energy of the gas. I cannot extract any more energy at that point, right? So because the pressure go down to equal to the ambient pressure, so I cannot push something at that point, right? Because the pressure is equal for both sides. Okay, so in this sense, I can say that the exergy of the gas inside the cylinder นะครับ the exergy of the gas inside the cylinder is less than the internal energy. Is less than the energy that I have in the system. Okay, internal energy. All right, because the limit is the atmospheric pressure outside here. Okay, so the potential to do work is less than the work that I have, in the system. Okay. All right. And to calculate the exergy or to calculate the work, the maximum work that I can convert, the maximum mechanical energy that I can have from this system is referred to this equation. All right, I will not show you the detail of the detail of the math proof here, but finally you will use this one to calculate exergy of this system, and it depends on here the internal energy of the gas at the initial state. This U0 is the internal energy of the gas at the final state. Okay, so if the gas reach P0 T0, then it has the energy of U0. All right, so you can plug in those number, and P0 is the atmospheric pressure. Okay, V0 is the final state of the volume of the gas. V is the initial one. S is the entropy at the initial state. S0 is the entropy at the final state. All right, so easy. Okay, let me show you some example. So if I have, for the first case นะครับ if my entropy of the gas นะครับ S1, if my entropy of the gas S1 equal S0. Okay, S0 is the entropy at the final state นะครับ if S1 is equal S0 นะครับ then I can isentopically expand the gas from the initial state down to the dead state, okay, down to the final state. And then from this process, I will have T0 and P0 at this point, at the same point, all right? So if S1 is equal to S0, I can just only expand the gas to reach the final state, okay? And then the work produced is equal to the exergy of the system, all right? In that case, okay, in this case, the last term will be 0, okay? All right, okay. And for another case, so if I have S1 greater than S0, another example, if I have S1 greater than S0, okay, so it means that if I isentopically expand the gas, I will reach the P0 if I isentopically expand the gas. This is TS diagram, and I am at the initial here, the gas inside the cylinder at the initial state, T1, S1, and I isentopically expand the gas S constant during the process, right? So I go down here, then I will reach the P0 before T0. So I will reach P0, but my temperature still higher than T0 นะครับ my temperature here, right? Here if you see the graph, so I hit the P0 constant pressure line here, but the temperature is still higher than T0, all right, at this point. So if I have the case that S1 greater than S0, so I can extract more work by connect heat engine to it. So because if I just only expand the gas, I still have higher temperature than T0, right? So I can extract more work by connect heat engine to the system, and I transfer the heat in the same time expand the gas, in the same time expanding the gas, okay? So in this way I can have useful mechanical work from the expansion, and also I have additionally useful work from the heat engine, all right? Okay, so the process will be the red line here. From the point 1, I just losing heat to the heat engine, right? So the entropy is decreased, follow the red line along the way, down to the dead state P0 and T0, okay? So in this way, I can extract more work from heat engine, right here, okay? So I hope you understand. So, and for this case, this term will not equal 0 because I got the difference between entropy at the initial state and entropy at the final state, right? So this term will not equal 0 for this case, all right? So hope you understand. Here, just practice to use this equation. I will show you the example in the next lecture. Okay, and if you want to find the exergy change, you can just put the state here, 2 and 1, and exergy change can be easily found, right? And you can add the kinetic energy and potential energy to the exergy. But normally this 2 is equal to 0, right? Because your system is normally stationary. Okay, but if you have velocity, you have to include the kinetic energy here. So you can write it in the full form like this. Okay. And next is the exergy of a flow stream. So for the exergy of the flowing fluid, you have to add flow work, PV, right? Flow work. If you imagine that you have to connect the piston to the flowing fluid, so you can extract this extra energy, right? You can extract this flow energy to do a useful work, okay? Extract the flow energy to push something. So the Exergy equation would be similar to the closed system, except that you have to add flow work term, okay? So this is the Exergy equation of the closed system or non-flowing fluid, right? And you add the flow work here on the right side, okay? And finally, you can rearrange PV and U to have H here. So the flow Exergy will be right by this equation, can be right by this equation, okay? So you have these two important equations. Okay, and we will going to do some example next lecture. Okay, bye bye for now.